Hey everyone, today we're going to take a journey deep into the hidden infrastructure of the internet. We're talking about the high-speed express lanes our data travels on every single day. We're pulling back the curtain on a technology that makes so much of modern life possible, something called MPLS.
So let me ask you this. What if your data didn't have to sit in digital traffic jams with everyone else's? What if it had its own dedicated VIP express lane just blowing past all the congestion to get where it's going faster and way more reliably? Well, that's pretty much the exact problem MPLS was designed to solve. So, here's our game plan for today. We're going to follow a single data packet on its special journey. First, we'll get a handle on why these express lanes are even necessary. Then, we'll learn the simple language of its labels, see how its secret path gets built from the ground up, and then we'll track it all the way to its final destination.
Okay, first things first. Let's look at the big picture. What exactly is this express lane system? And why on earth does the internet even need it?
At its core, MPLS stands for multi-protocol label switching, which I know sounds super technical, right? But the key idea is actually really simple. It's all about the labels. Think of it like a special shipping label system for your data. Instead of a mail carrier having to read a long, complicated address at every single stop, they just glance at a simple code that tells them exactly where to send the package next. This makes forwarding data incredibly fast and way more efficient.
And believe it or not, this entire powerful system runs on a really simple language, made up of just 3 core actions: push, swap, and pop.
First up, we've got push. This happens the second a normal data packet arrives at the edge of the network. It's like it's getting its VIP entry pass. The first router it meets literally pushes an MPLS label onto it, officially welcoming it to the express lane.
Next up is swap. Now, as our packet zooms through the network, each router it meets doesn't have to do any heavy thinking or complex lookups. It just looks at the incoming label, swaps it for a new one, and sends the packet along to the next stop. It's a super fast handoff, happening over and over at every hop.
And finally, we have pop. As the packet is just about to leave the express lane, that final special label gets popped right off. The VIP pass is removed, and the packet is returned to its original, pristine state, all ready for its final delivery. Okay, so push, swap, pop. Simple enough, but wait a minute, how does the network know which label to swap for which? I mean, how are these secret express lanes actually created in the first place?
Well, it all starts with a concept called a forwarding equivalence class, or FEC for short. It's a mouthful, I know, but it's really just a fancy term for grouping similar types of data together. For example, all the traffic going to a specific web server, or maybe all the voice calls from a particular office. They can all be grouped into the same FEC. Just think of it as a sorting bin for data packets.
So once the network defines a category, an FEC, it then builds what's called a label-switched path, or LSP, just for it. And this is the actual pre-planned one-way express lane we've been talking about. It's basically a virtual tunnel built specifically for that type of traffic to travel through the network at top speed.
So how are these paths actually built? Well, networks use a few different protocols for the job. The most common one, LDP, is kind of like your GPS on its automatic setting. It just finds the shortest path available. But for really critical traffic, like a live video stream, engineers can use a protocol like RSVP to basically engineer a custom, high-performance path and even reserve a dedicated chunk of bandwidth for it. That's how you guarantee quality.
All right, we've got all the pieces of the puzzle. Now let's put it all together and follow a single data packet on its complete journey from start to finish through the MPLS network. So let's trace its path. First, an ordinary IP packet arrives at what's called the ingress or entry router. That router sees what kind of packet it is, figures out its FEC, and pushes the first label on. From there, it's sent into the core of the network, where at each and every hop, the label is swapped for a new one. This happens again and again, incredibly quickly. Finally, the packet reaches the second-to-last router in the path, which pops the label off. This leaves the very last router with a simple job: just forward the original, clean IP packet to its final destination.
Now that whole middle part of the journey, that constant, relentless swapping, that's where the real magic of MPLS happens. That's the secret sauce. Because the routers deep inside the network don't have to do complex lookups on IP addresses, they just swap labels. It's a much simpler operation, which makes the whole process unbelievably fast. This is truly life in the fast lane. Okay, now let's zoom in on that final step, the pop.
There's a really clever optimization here called penultimate hop popping, which just means the second-to-last router is the one that removes the label. Now, why would you do it one step early? Well, it saves the final router a job. That last router doesn't have to waste any processing power dealing with the MPLS label. It can focus entirely on its main job, delivering that IP packet. It's a small detail, but it's all about maximizing efficiency.
Now that all makes sense for a pretty simple journey, but what happens when things get more complicated? What if a packet needs 2 shipping labels? One to get it across the country and a second one to get it to a specific person's desk inside a giant corporate office.
This is where MPLS gets really clever, with something called label stacking. You can think of it like those Russian nesting dolls. MPLS can stack multiple labels on top of each other. The outer label is for the main journey. It guides the packet through that high-speed express lane, the LSP. Once that journey is done, that label gets removed, revealing an inner label. This inner label has the final specific destination info, which is absolutely crucial for services like VPNs. And there's even a tiny S bit, which is just a signal that tells the router, hey, you've reached the last label in the stack.
So, when you boil it all down, what's the big takeaway here? MPLS wasn't just some neat technical trick. It was a fundamental upgrade for the internet's plumbing. It created a faster, more flexible, and way more reliable way to move data across huge networks. It really became the invisible foundation for services we all use every day, like secure corporate VPNs and high-quality video calls.
So MPLS built the invisible express lanes for its generation of the internet, and it solved critical problems of speed and scale. But this leaves us with a pretty big question to think about. As our demands on the internet continue to explode, what will the next generation of its architecture look like? And what new problems will it have to solve?